Hello and welcome to topic number 8 in this OCR GCSE in Computing series. We're looking at, in this video and the next couple, maybe 5 or 6 videos, we're looking at data representation, all about binary, hexadecimal, all of those lovely topics, and the specification fortunately splits it up for me into several nice chunks. The first chunk, I should say, is about units, and we're looking at some fundamental things absolutely essential for you to nail this course. You know about this stuff. We're doing a quick recap because we looked at binary already in topic number 2, which is about binary logic and logic gates, and part of that video, not all of it, is about binary and what binary is. So let's have a quick recap. So binary is what is known as a base 2 system, and base 2 essentially means that it only uses 2 digits. It's surprisingly hard to say digits in this video. Anyway, the 2 digits used are 0 and 1. And an example of a base 10 system is dinary, and dinary is what we use on our everyday basis. We use digits 0 to 9. If you count them up, that equals 10. Hopefully you can do that maths. So 2 digits in binary, 0 and 1, and they're used in computers. Computers represent everything with binary. It's a really important concept that computers only represent data in binary, and that's because binary symbolizes voltage. A computer is an electronic device. It has 2 states, off and on, and 0 represents off, 1 equals on, and that's why it's used. It symbolizes voltage, and it represents the 2 states that computers can be on. And the reason why another reason why it's represented in binary is because it has to be converted from analog. So analog data is what we experience on a day-to-day basis. Analog data is sort of the constant streams of data passing around constantly. This is a spelling that I think the English spelling is with a U. That's how I would spell it, U and an E at the end. But analog is spelled like this usually in an electronic context. It's sort of the American spelling that's used in electronic contexts. So I'm using it for this video. It doesn't matter how you spell it. So a computer cannot understand this analog data because there are no real bounds. So an example of analog data is sound. Sound can have huge highs, it can have huge lows, and a computer doesn't like this. It likes to have these 2 options because it represents the most fundamental aspect of itself, because it's it being on or off. It doesn't like that you can have sort of infinite amounts of data, analog data, or barely any of it. It doesn't like that, and so it must be converted into digital data before analog is used, because analog can't be used by it. So in digital, everything is defined as digits, which are numbers, and for binary, digits are either 1 or 0. So all, if not most of digital data is in terms of binary, and a binary digit is called a bit, and we're looking at that in the next slide. But briefly, let me just recap this. So we don't need to know, the spec doesn't mention analog and digital data, but it's the most fundamental thing you understand. If you take anything out of all these videos, all 23 videos, it's this slide. I really want this to come across. A computer needs to represent things in either 2 states, off or on. It cannot represent things in terms of analog data, which is sort of random, huge, it's difficult to visualize, but huge streams of data which we experience on a daily basis. Humans are incredibly intelligent. Our brains are so complex and so well evolved that we understand different bits of data. A computer is not as smart in that sense. It can do huge calculations, but it's not as smart as humans, and so it needs this simple representation to work. So we've got to learn maybe 5 or 6 incredibly key terms. You've got to learn this slide. And the first of which key term is a bit. Like I mentioned, this stands for binary digit. This bit is just derived from binary digit. If you sort of merge the words together, it forms a bit. And a bit is simply either 1 or 0. So an example of 1 bit is 1. Or example of, you can have, so 2 bits would be 1 or 0, or 0, 0, or 1 and 1, etc. So a nibble is simply 4 bits. We don't really use nibble too much, but you are required to know about it. A nibble is 4 bits. For example, 1, 0, 1, 1, or any combination of 1 or 0. A byte is what we use mainly because a bit is so small, and we use different powers of bytes. So a byte is 8 bits or 2 nibbles. Example is as follows there. So like I say, we use prefixes to make them bigger because a byte on its own is small, and we use these prefixes to label file sizes. So a kilobyte is 1000 to the power 1 bytes. 1000 to the power 1 simply means 1000. An example of this would be if you had a question that asked you to represent 52 kilobytes in terms of bytes, you'd do 1000 to the power 1 times 52. So then a megabyte is logically 1000 to the power 2. So this means it's 1000 times itself, which is 1 million, I believe, although that's not really that important to know. An example, if this was 52 to the megabyte, and you wanted to represent it in bytes, you do 1000 to the power 2 times 52. And you don't have a calculator in exam, so I'll show you a tip next how to calculate these. They're really simple, actually. But gigabyte is 1000 to the power 3, and a terabyte is 1000 to the power 4. I've noticed a mistake, that should be a T to represent that. So a way of working this out is after a kilobyte, simply 3 zeros are added each time. So it goes from 1000 to a million to, that's probably a billion, maybe not, but you can see it adds 3 zeros. We get a nice pyramid if we add them together. 3 zeros each time, and that should make it slightly easier. You simply, if you get a question, you simply times it by how many you've got to work out how many bytes you have. Fairly simple, I think, this video. Make sure you learn it because it's very fundamental, and we will be using it in the next couple of videos. So thanks a lot for watching, and hopefully I'll see you next time.